All right, let's dive right into this explainer, where we're going to break down the sheer engineering, physics, and software that actually power modern quadcopters. Now, if you've ever watched a drone just seamlessly hover in midair or dart effortlessly through a really dense obstacle course, you know it absolutely looks like magic. But today, we're pulling back the curtain. We're going to strip away that plastic shell and look under the hood at the absolute engineering magic that makes it all possible. What we're really talking about here is a flawless symphony of microelectronics, instantaneously reacting physics, and insanely complex spatial algorithms all working together in fractions of a second.
And to really wrap our heads around the fact that these are extreme, high-performance machines and not just, simple toys, we have to look at the staggering extremes they can reach. 685 kilometers per hour. That is the current world speed record for a battery-powered remote-controlled quadcopter. It was set by Benjamin Biggs and Aidan Kelly down in Australia back in May of 2026. I mean, just think about that for a second. That is literally faster than a Formula One car going full throttle down a straightaway. It's actually faster than some private jets cruising in the sky. Hitting that kind of blistering extreme performance requires an absolute mastery of both hardware and software working in perfect unison.
So, here is our roadmap for today's explainer. 1. The quadcopter revolution. 2. The physics of flight. 3. Powering the propulsion. 4. The brains, which is PID control. And finally, 5. Mapping the unknown with SLAM.
Let's kick things off with Section 1, the quadcopter revolution. From clunky prototypes to modern marvels. Believe it or not, the concept of four-rotor flight actually predates the modern microchip by nearly a century. Pioneers were experimenting with these radical designs super early on. Way back in 1908, Louis Breguet achieved a tethered flight with a four-rotor design. But honestly, it was this massive, terrifying, chaotic contraption. They literally had to hold it down with ropes just so it wouldn't immediately flip over and destroy itself. Then in the 1920s, Etienne Oymachan pushed the boundaries to set distance records. And by 1923, the US Army Air Service was testing the massive Day Bothazzat helicopter. The problem was, these early mechanical beasts were hopelessly complex. They were incredibly heavy, way underpowered, and pretty much impossible for a human to pilot because they completely lacked any digital stability augmentation. Fast forward through decades of vital electronics advancements, and the concept finally evolved into the sleek, modern machines we know today. A huge milestone was the groundbreaking 1999 Dragonflyer, which was one of the very first multi-rotors produced in significant quantities that could actually successfully carry a camera.
And when you look at the recent numbers, it's wild how rapid the technological leaps have been in just the last few years. We're charting these massive, unprecedented jumps in the Guinness World Records for battery-powered quadcopters over an incredibly tight window of time. We go from Ryan Lademan hitting a very impressive 360 kilometers per hour in late 2022 to Luke and Mike Bell completely shattering that by jumping to 657 kilometers per hour in 2025, right up to that unbelievable 685 kilometer per hour record in 2026. This exponential curve isn't just about slapping bigger batteries onto carbon fiber frames, right? It's the direct result of highly optimized propulsion and highly intelligent control systems evolving at lightning speed.
Which brings us to Section 2, the physics of flight, mastering the air.
So you might be wondering, how do these machines actually maneuver through the air with such blistering speed and precision? Well, if you picture a conventional helicopter, you know it absolutely relies on a tail rotor to prevent the main body from just spinning wildly out of control. Basic physics, right? Every action has an equal and opposite reaction. But quadcopters completely lack tail rotors, so that introduces a rather massive, kind of mysterious design challenge. How do they counteract that immense rotational torque, and how do they actually steer?
The solution is just an incredibly elegant display of physics in action. Quadcopters generally have two rotors spinning clockwise and two spinning counterclockwise. When all four spin at the exact same speed, the net torque is perfectly zero. It cancels out the spin and keeps the drone perfectly straight and stable. Now, if you want to yaw, meaning turn to the left or the right, the drone simply speeds up the clockwise rotors and slows down the counterclockwise ones, or vice versa. This purposefully unbalances the torque just enough to rotate the craft. For pitching forward or rolling to the side, it uses something called differential thrust. Think of differential thrust exactly like paddling a canoe. If you paddle a lot harder on the right side of the canoe, the boat naturally shifts and turns to the left. The drone does the exact same thing in the air. It speeds up the rotors on one side to lift that side up, physically tilting the entire vehicle and shifting the net center of thrust exactly in the direction you want to travel.
Okay, moving right along to Section 3, powering the propulsion, electronic muscle.
Now, to execute those rapid, incredibly precise shifts and thrusts without instantly falling out of the sky, the drone needs some serious electronic muscle. The propulsion system relies on a highly integrated network of components working in perfect sequential unison. It all starts with the power from a high-discharge lithium polymer, or LiPo, battery. That battery floods massive amounts of power into the electronic speed controllers. These controllers, in turn, drive the brushless direct current motors, which actually spin the propellers. And every single electrical pulse of this operation is orchestrated by the flight controller. Choosing brushless motors over older brush designs was an absolute game-changer for this puzzle. They offer much higher electrical efficiency, vastly superior torque-to-weight ratios, and a significantly longer operational life because there's literally no internal physical friction wearing the motor down.
So let's talk about the electronic speed controller, or ESC, because it acts as a really critical translator here. The battery provides direct current, but the high-performance brushless motor actually requires a three-phase alternating current signal to run. So the ESC uses rapid-fire electronic switching, specifically this ingenious technique called pulse width modulation, or PWM, to constantly adjust the effective voltage reaching the motors. Think of PWM like flicking a light switch on and off dozens of times a second just to dim a light bulb. The ESC is doing exactly that with raw electricity to control the motor's speed with ruthless, absolute precision, and it's responding in mere fractions of a second to commands from the flight controller.
And here's where it gets seriously cool. Modern ESCs often use this incredibly clever trick called sensorless commutation. Instead of relying on heavy physical sensors inside the motor to know the exact position of the spinning magnets, the ESC detects something called back EMF. Back EMF is essentially the electrical feedback that's automatically generated by the spinning magnets themselves. It's almost like the motor is actively whispering back to the computer through tiny electrical pulses. By listening to this feedback, the drone basically uses the motor itself as a ghost sensor. Stripping away those physical sensors removes unnecessary weight and significantly boosts the efficiency and reliability of these unmanned aerial vehicles.
Let's jump to Section 4, the brains, otherwise known as PID control.
So, we have 4 independent motors constantly fluctuating in speed to balance torque and shift thrust. But how on earth does the drone actually know if it's flying level? Well, the flight controller relies on a mathematical algorithm called PID, which stands for proportional, integral, and derivative control. This closed-loop feedback system is the hidden magic that maintains perfect roll, pitch, and yaw stability against sudden gusts of wind or unexpected physical disturbances. Without PID actively managing the flight, flying a quadcopter would be exactly like trying to balance a heavy broomstick upright on the palm of your hand during a windstorm. It would constantly and violently flip over before you could even react.
Here is exactly how that brilliant loop functions. The flight controller continuously reads real-time physical data from an onboard inertial measurement unit, which is tightly packed with microscopic accelerometers and gyroscopes. The PID algorithm is constantly comparing this actual orientation of the drone against the desired orientation requested by the pilot's stick movements. So, if a random gust of wind knocks the drone even a millimeter off kilter, the PID controller instantly calculates the exact mathematical error and fires off the perfect corrective motor speed commands to the ESCs. All of this sensing, calculating, and correcting is happening thousands of times a second, completely invisibly, creating that perfect illusion of effortless hovering.
Finally, Section 5, Mapping the Unknown with SLAM.
Let's move to our final layer and see how all this builds into full autonomy when we remove the human pilot from the equation entirely. This brings us to SLAM, simultaneous localization and mapping. This is the absolute cutting-edge robotic framework that basically gives a drone its own independent nervous system. It allows it to navigate complex, obstacle-filled spaces it has literally never seen before. We're talking about flying through the pitch-black inside of a collapsed building or navigating autonomously through a dense, unpredictable forest at high speeds.
Now, SLAM is famously described in robotics as the ultimate chicken and egg problem. Think about it. To get an accurate physical location, a drone fundamentally needs an accurate map of its surroundings. But to build an accurate map of its surroundings, the drone absolutely needs to know its exact physical location. So how do you possibly solve a mathematical problem where both requirements entirely depend on each other?
Well, the drone solves this paradox by building the map incrementally, usually using highly precise sensors like LiDAR or depth cameras. It starts at an origin point, taking a massive initial measurement. Then, as it moves, it measures new, unknown areas.
By rapidly comparing the overlapping data between the old scan and the new scan, it dynamically calculates exactly how far it has moved. But here's the catch. Incredibly small calculation errors inevitably build up over time. It's a phenomenon known as drift. To fix this, SLM utilizes a brilliant concept called loop closing. Think of loop closing exactly like wandering, totally lost in a sprawling city, accumulating wrong turns, until you suddenly look up and recognize a famous landmark, like a massive clock tower you saw earlier. In that instant, your internal map immediately snaps back into perfect focus. When the drone recognizes a distinct feature it has previously mapped, it mathematically snaps its internal map back into alignment, instantly correcting all those accumulated drift errors.
And what makes SLAM so profoundly revolutionary for drones is that it provides absolute autonomy without requiring any external signals whatsoever. Because it relies entirely on its onboard sensors to constantly measure relative obstacles, a SLAM-equipped drone can safely navigate completely unknown, GPS-denied environments. This is a massive deal in robotics. It doesn't need satellites way up in space to tell it where it is. It brilliantly figures it out all on its own, whether it's deep underground, indoors, or completely off the grid. When we step back and combine this high-speed, torque-canceling physical design with brilliant PID mathematical stabilization and autonomous SLAM navigation, we really have to look up and wonder what's next. The transition here is just astounding. This technology has successfully scaled from tiny plastic toys to massive professional camera rigs. So, are human-carrying electric vertical takeoff and landing vehicles, like those massive battery-powered quadcopter air taxis Airbus is currently developing, just around the corner for everyday urban transport? Because the foundational software and physics we've explored in this explainer today are absolutely already there, and scaling them up is the profound leap currently happening right before our eyes.
So the next time you see a drone hovering effortlessly above you, you'll know it's not just some flying piece of plastic. It is an absolute marvel of instantaneous calculus, high-frequency power modulation, and spatial mapping. Thanks for exploring the anatomy of a drone with us in this explainer. We really hope you walk away with a profound new appreciation for the engineering magic buzzing around in the sky. And honestly, it leaves us with one incredibly exciting thought. If an autonomous flying machine can map the unknown and master the physics of the sky perfectly on its own today, how soon until you're the one sitting inside it?